everybody, and welcome back to Environmental Science 101. So here we talk about Earth's heat and temperature, and its air temperature, and where that comes from, right? This guy. Okay, so, real quick, this is not essential information here. We don't need to worry about all the details here at all, right? What I want to point out, planets have a life cycle. They're born, and they're young and hot, like we saw with the creation of the solar system. They get older, they lose that heat, they get colder and older, and then they die, right? Death, in the case of a planet, means that it basically stops changing on the surface, right? So, like our moon is dead. It's small, it didn't have that much heat to begin with, and it loses it quickly because it's lower mass, right? So if you were to look at the moon, it's pretty much dead. Mars is mostly dead, right? Some things, Vesta and Io and other bodies, are not just warm, but like incredibly hot, like completely magma. It's like a Super Mario level, right? Io gets tossed around by Jupiter, basically bullied 24/7. That's why it has this. Venus has really, really high temperatures, right, but is smaller than Earth, so it's complicated. And then here's our Earth in the middle. It's alive. It's in its very most active and important stage here. It's not dead. Awesome. Why would I bring this up? Well, because most of the time, all right, if you ask people the question of why it is cooler at higher altitudes, right? Like if you climb up on a mountain, why is it cooler up there? Most all of them will tell you what? Oh, it's because you're further away from the Earth, and the Earth is hot, and look at that. Okay, right, which is wrong. It's not correct. Okay. Atmospheric temperatures do not depend on any of this stuff that's going on with Earth's heat or its interior. Why would we talk about this? When it comes to climate change, being able to rule out causes of the atmosphere getting warmer becomes important, all right? So this idea that going up to higher altitudes, you know, that you're further from the Earth, and that's why the temperatures go down, it's wrong, right? It's gone. What are we going to replace it with that is our better kind of mental picture, mental model or understanding? There's a little bit of a chain of events on this one, but it's not too bad. Okay, it's not from being further from the core of the Earth or anything like that, right? It is due to the decompression of the air, right? So at sea level, right, you have a certain mass of air that is pressing down, right? Air pressure. You go up, right, and the amount of air that's like pushing down goes down, right? Until, you know, if you're at the top of the mountain, right, you've only got this much air pushing down instead of this much, right? We have less air pressure. The air starts to spread out. As it spreads out, right, the average kinetic energy of the molecules gets lower, right? We talked about how temperature is about the average kinetic energy of the little particles moving around. Okay, well, without that pressure, the particles start to move further and further and further away from each other. We have less mass occupying the same area that it used to occupy. Energy goes down, heat goes down as a result, right? Higher altitude means less pressure, which means lower air density, which means fewer molecules that are moving around and hitting stuff and transferring their energy, which means less heat energy transferred, which means lower temperatures. Awesome. This is going to lead into our idea of atmospheric temperatures, right? So what are the most important things in determining what the temperature is going to be in some place on the planet? And if we stopped and thought about it, we would say, okay, well, the first thing is, you know, are we at the North Pole or the equator, right? Call that one latitude, right? How far away you are from the equator, how far north or south you are. Other factor is going to be elevation, right? Are we sitting at the beach, or are you at the top of Mount Everest, right, where it is super cold? These are going to be the two factors that matter the most as far as atmospheric temperatures or air temperatures all over the world, right? And couldn't, you know, get a worse diagram than this, honestly, but it's actually perfect for our purposes, right? So red stuff is going to be warmer, blue stuff is going to be cooler. We notice that there are some outliers. Mountain ranges here, this is the Himalayas, which includes Mount Everest. You notice it's way colder than the stuff around it. You can see the Alps here. You can see a little bit in Appalachia, right? But other than the elevation of the mountain ranges, it's really about how far away you are from the equator, right? Awesome. So I'm going to take a moment here. We're going to do the super fast forward version of this. But essentially, right, you can try to calculate based on the amount of energy, amount of light that's coming off the sun, and what we know about the Earth, right? How far away it is, how big it is, how much of that solar energy is going to get intercepted, right? With those two factors in mind, we could sit down and be physicists and crunch the numbers and figure out what the temperature of the atmosphere, quote unquote, should be. All right. The actual, yeah. Again, don't worry about any of these details at all. All right. If anybody wants to check this, that's fine. I used to make students do this actually as part of a lab. Yeah. So we're going through that process I talked about, right? So the sun emits a certain amount of radiation, which we know. The Earth intercepts a certain amount of that radiation, which we can understand, right? Spread out throughout the whole atmosphere. Awesome. Some of that is going to bounce back into space. Some of it's going to be absorbed by the Earth, right? And based on how much radiation comes in and how much the Earth holds on to, how much is reflected versus absorbed, we can crunch all the numbers, and I promise these are all correct, professional, right? And your final answer that you would get for the air temperatures of the entire Earth is a negative number. Is that what actually happens? Is most of the Earth at negative temperatures? No, right. So the reason why I'm going through all of this, the whole purpose is to show that physically, like mathematically, there has to be some other sort of warming force happening in the atmosphere, all right? That, you know, this thing we're about to talk about that I haven't said the name of, right, wasn't just invented, right? That it has to be true, essentially. That there's no way to make a model of the Earth that makes sense without this thing, right? And this thing is the greenhouse effect, which maybe we have heard of. So what's the idea on this one? Now, real quick, this tends to be among the very most misunderstood things that we cover in the entire course. Same for evolution, right? And the reason why is because people come in thinking that they got it, thinking they know every detail, when they actually kind of only know this more simple version, right? Not the real thing. Okay, so what is the real thing? It's exactly what's going on here. I do love this diagram, so thank you to World 101. Sun's radiation comes out, all right? Radiation here is the same word as light or heat or energy, basically interchangeable for now, right? Comes in, right? Now, some of it is going to be reflected or absorbed off of cloud cover, which we will mention again in a bit. Rest is going to reach the Earth, all right? It is absorbed by the Earth, and then it is re-radiated. So we mentioned how everything, right, is always emitting light, right? That I'm always emitting light, you're always emitting light, right? Just in a spectrum that we can't see, infrared. Earth is doing the same thing, right? So it is re-radiating heat, light, and energy back into space. Now, some of what it absorbs and then re-radiates makes it all the way out into space. Some of it hits these things in the atmosphere, which are called greenhouse gases, all right? And when it hits those, right, after having hit the Earth, been absorbed, and then been re-radiated in a lower wavelength, higher wavelength, lower energy, right? It's going to hit the Earth, go back, and get scattered by greenhouse gases in the atmosphere. They don't just send it back to Earth, they scatter it in all directions, which is why the blanket metaphor is actually not really a very good one, right? But it has the effect of increasing Earth's temperatures, all right? And this is the reason why the atmospheric temperatures are not negative 18°C all over the world, right? It's more like 14 to 18, right? Why we don't have negative temperatures everywhere is because of the greenhouse effect. You have to have this, or else Earth is completely frozen over and you don't get life. All right. We don't need to necessarily worry about the technical stuff here. What are we actually looking at, right? So, Earth is emitting radiation, right? It's emitting radiation at all these different wavelengths, high and low, right? So this is going to be our high energy stuff here, right? Low energy stuff over here. And our y-axis is the intensity of it, right? So Earth is emitting all this stuff, right? Here's its highest intensity, all of here, right? Peaks, right, for a body that is 14°C, which is our average atmospheric temperature, right? Go to peak in the infrared spectrum. Now, this curve that I keep going over with the yellow, this would be like the mathematically ideal, theoretical, perfect emissions, right? Where we talked about, okay, Earth, light hits it, re-radiated back out in the infrared, right? This would be what it emits in a perfect world. But that's not what actually happens, right? Because those greenhouse gases in the atmosphere absorb and re-radiate this stuff, or scatter it, right? So these are different greenhouse gases that are labeled here, right? So water vapor is actually going to be by far the most significant of the greenhouse gases, though it's not something that we are necessarily concerned with as human beings, right? Methane, we might have heard of as being one, right? Ozone is one as well. We're not going to worry about it for now, right? here's carbon dioxide, right? So what these bands represent, right, are wavelength bands of light that these gases will block, right, from reaching space and scatter in all directions, right? So basically what's happening here, right, is that the gas, water vapor, is blocking all of this from escaping, right? It's blocking all of this radiation that would be escaping from Earth, scattering it in all directions, and then here, right, where we have no greenhouse gases blocking, we get a lot of intensity sent back out from Earth. So, as more greenhouse gases are added to the atmosphere, like carbon dioxide, this becomes more intense, right? More of the heat is scattered, comes back, and the atmosphere warms as a result. The basic mechanism here behind the greenhouse effect has to be there. It is inarguable. There are other factors, though, right? So some of the sunlight that comes to Earth is going to be reflected by things like ice sheets, right? Put back into space. The percentage of the light which is reflected back out is this thing called the albedo, right? Answers this question. What fraction of sunlight is reflected and not absorbed? Certain things have a really high albedo, right? So snow, things that are going to be white, right? Like ice sheets in general, right? And snow will do this. Clouds will do this as well, though, as we'll see in a bit, it's a little bit more complicated with them, right? Stuff that doesn't reflect much light, but absorbs it, right, is going to be water. And we don't have it on here, right? But something like concrete or asphalt is going to be absorbing a lot of it and reflecting very little. This is good. We want higher albedo. We want light to reflect out because that's going to mean that less of it gets absorbed into the air and raises our temperatures here, right? And we notice, right, July, right, albedos, generally speaking, tend to be much lower. Whenever we have winter months, right, they tend to be much higher, generally speaking. Awesome. So, because of variation in carbon dioxide and other greenhouse gases, as well as some other factors, but primarily due to these, Earth's temperature has changed over time. It has been through phases of ice ages, or being completely frozen over. It has been through phases of hothouses, or being really hot. We don't need to really remember all the details here, but what we do need to understand is that Earth's temperature and global climate has changed a lot, all right? It wasn't always an ice age. There wasn't always ice sheets at the poles. It has gone through these different periods of being much hotter than it is today, or much colder than it is today. And it is also known for those different hot or cold periods how much carbon dioxide there was in the air. And the coupling, right, the strength of the relationship between those two is really strong. Here's another one, right? So here is carbon dioxide, right? ppm is a measure of concentration, right? Here is methane, right? These are greenhouse gases. And then here is our temperature, right? Just notice how strong these are correlated here. I mean, it's basically perfect, right? This is thousands of years before 1850, right? So the last 500 years of Earth's history. 500,000, yes. Awesome. We notice that these are extremely strongly correlated as far as greenhouse gases and temperature. We also notice, right, that temperature tends to increase really quickly and then decrease really slowly, right? And then increase really quickly and then decrease really slowly, which is bad news for us. This just reinforces yet again. So this is looking mostly at sea ice and historical data, right? We've got temperatures down at the South Pole, right? And then CO2 concentration. And what I really want you to get out of this is just to see how strongly these are coupled. Earth's temperature has changed over time, largely as a result of changes in carbon dioxide. That's why. And that's the main point here. And now we're ready to move on to the effects of excess greenhouse gas and excess heat on the environment and on the ocean.